welcome to the brief introduction to mass spectrometry. Now, if you're not a science major or simply not familiar with this topic, you might think mass spectrometry is hard to understand. But if you take a closer look, you will find that the physical principles behind mass spectrometry are quite simple. The idea of mass spectrometry bloomed in the early 1900s. Since then, mass spectrometry has experienced many revolutionary improvements. Nowadays, there are at least dozens of different mass spectrometers for different purposes. However, no matter what differences they have from one another, almost all the mass spectrometers share the same basic principle, that is to separate ions according to their mass and charge, particularly mass-to-charge ratio. There are three basic components in the mass spectrometer: the ion source, the mass analyzer, and the detector, corresponding to three of the four major processes in mass spectrometry: ionization, mass selection, deflection, and detection. Ionization is a process where the neutral molecules you want to study are turned into charged ions. Mass selection is where magnetic field and/or electric field is applied along the ion's traveling pathway to alter the speed and direction. And detection is where we acquire the information we need. Here is a simple animation of how mass spectrometry works. The molecules are first broken down to pieces, accelerated and deflected by a magnetic or electric field, separated based on their mass-to-charge ratio, and finally detected by the detector. However, mass spectrometry cannot be simply summarized into this little animation. As mentioned before, many improvements have been made through the years, and at least a dozen techniques are available for each of the processes. Now, let's have a look at some of the different techniques. The first thing you want to do in mass spectrometry is ionization. Electron ionization is probably the earliest ionization methods used. The idea of electron ionization is to let electrons bombard the gaseous molecules to form ions, or break them down to charged fragments. The electrons are produced by heating and passing a current through the filament, or cathode, and accelerated through the chamber by their attraction to the anode. A magnetic field is applied to let the electrons have a helical pathway to increase the possibility of colliding with the molecules. In the mid-1930s, spark ionization was invented. This method is often used to produce gas phase ions from a solid sample. The spark ion source consists of a vacuum chamber containing the electrodes, which is called the spark housing. The tips of the electrodes are composed of or containing the sample and are electrically connected to the power supply. The electrodes create an electric field that accelerates the generated ions through the exit slit. The prepared solid sample is vaporized and partially ionized by an intermittent discharge or spark. In the 1950s, chemical ionization was introduced. This method is quite similar to electron ionization, but instead of using electrons to bombard the molecules directly, the electrons collide with a kind of reagent gas and ionize the gas first. Then the charges are transferred from the reagent gas to the molecules by chemical processes. This process has a lower energy than electron ionization and thus will produce lag fragmentations, so we can easily find out which signal represents the molecular ion. Electrospray ionization was invented around 1968. The liquid containing the analyte of interest is dispersed by electrospray into a fine aerosol. The solvent evaporates from a charged droplet until it becomes unstable upon reaching Rayleigh limit. So what is Rayleigh limit? A droplet tends to have a spherical shape because of the surface tension of the liquid. If it is electrically charged, the electrostatic repulsion between the ions might overcome the surface tension, leading to its breakup. Upper estimates for the charge in the sphere are given by the Rayleigh limits. So the droplet undergoes Coulomb fission, meaning the original droplet explodes, creating many smaller, more stable droplets. The new droplets undergo dissolution and subsequently further Coulomb fissions. Eventually, there will be just one molecule in one droplet, and the molecular ions will form when the solvent evaporates. And the last ionization method we're going to look at is MODI, the matrix-assisted laser desorption ionization, which came out around mid-1980s. In MODI, the analyte of interest is mixed with a large excess of a matrix compound that absorbs efficiently at the laser wavelengths. The matrix allows the energy from the laser to be dissipated and also assists with the ionization of sample molecules through electron transfer and chemical processes. MODI is a three-step process. First, the sample is mixed with the matrix material and applied to a metal plate. Second, a pulsed laser irradiates the sample, triggering ablation and desorption of the sample and matrix material. Finally, the molecules are ionized by being protonated or deprotonated in the hot plume of ablated gases. Now we're done talking about ionization. Let's move on to the mass selection. The oldest selection technique should be all kinds of sector instruments. For example, the magnetic sector. By applying a magnetic field along the pathway of the ions, the direction of the magnetic field at right angles with ions' velocity, the ions will take a circular pathway, and the radius of the pathway is determined by the mass-to-charge ratio. So, by scanning the magnetic field, we can detect ions with specific mass-to-charge ratio. In the mid-1940s, time of flight is brought into view. Time of flight is a kind of method where the ions are separated by the time they take to fly from the ion source to the detector. The ions are accelerated by an electric potential. Since the kinetic energies of the ions are solely given by the same electric potential, the speed of the ions vary according to the mass-to-charge ratio. The ions will then fly through a field-free flight tube, and the time they take will only depend on their mass-to-charge ratio. Moving on, the concept of the quadruple mass analyzer was first reported in the 1950s. A quadruple consists of 4 rods arranged in parallel, where those opposite to one another are electrically connected. A voltage of opposite polarity is applied to adjacent rods consisting of a direct current component and a radio frequency component. Ions are accelerated out of the ion source and between the rods. They experience forces that cause them to oscillate toward and away from the rods. When the oscillation becomes too large, the ions strike the rods and do not reach the detector. Only the ions in a certain range of mass-to-charge ratio are passed through the system, but changes to the potentials on the rods allow a wide range of mass-to-charge ratio values to be swept rapidly. In 1974, Fourier transform ion cyclotron resonance was invented. In a magnetic field, an ion with a velocity will adopt a circular trajectory perpendicular to the field. An ion cyclotron frequency depends on its mass and charge, but is independent of its velocity. So, the mass-to-charge ratio of an ion can be determined by measuring its cyclotron frequency. In a Fourier transform ion cyclotron resonance mass spectrometer, all ions in the trap are excited simultaneously to larger orbits by applying a wide range of excitation energies at once in the form of an excitation chirp. Applying the Fourier transform, the combined waveform can be devolved to a frequency domain spectrum from which a mass spectrum can be assembled. As a result, Fourier transform ion cyclotron resonance mass spectrometry can detect and measure the mass-to-charge ratio of all ions in the trap simultaneously. In the 1990s, there were ion traps. An ion trap is a combination of electric and magnetic field used to capture charged particles, often in a system isolated from an external environment. Popular ion traps include 3-dimensional quadruple ion trap, linear quadruple ion trap, and orbitrap. Finally, we come to the detection process. First, there was a Faraday cup. The Faraday cup is a long, thin, rectangular box where the ions will strike the base of the box. When positive ions strike the plate at the bottom, electrons will be drawn from the ground to neutralize the excessive positive charge. The movement of the electrons will cause a current, and the current will be amplified and recorded. After the Faraday cups, there are the electron multipliers. Electron multipliers achieve higher detection efficiencies than Faraday cups by amplifying the secondary electrons emitted from the detector surface. The internal surface acts as a resistor so that an electrical gradient is achieved across the detector. Ions entering the electron multipliers will collide with its surface and emit secondary electrons, and the secondary electrons will collide with the surface again to emit more electrons, causing a cascading effect. So when the electrons are at the tip of the detector about to enter the circuit, the current will be significantly amplified. And there you have it, a brief introduction to mass spectrometry. Please subscribe and comment below, and stay tuned for our future videos about the application of mass spectrometry.